Okay, hi everyone. My name is Colin. Talk was originally meant for the undergrad session. So if you find this too simple, then you can just sit back and relax. So currently, quantum computing is a very popular research topic, and many researchers are looking into potential qubits. One possibility is the electron spin, and in this project, I studied the relaxation process of an electron spin. Specifically, I studied the transverse relaxation. Transverse means on the xy plane, and relaxation is how the magnetization vector decays over time. Here we have a pulse causing an initial magnetization along the y-axis. When we have multiple spins, they eventually become out of phase. This process is known as relaxation. As spins interact with their environment, their precession rates change. This results in the exponential decay of the transverse magnetization, characterized by the time constant, T2. The main cause of electron spin decoherence at low temperatures is hyperfine coupling, which is when the electron and nuclear spins interact. There are two interactions involved, the first of which is spin-dipole. This is analogous to dipole-dipole interactions in classical E&M. The second is Fermi contact, which only happens when the electron and nuclear spins are so close that their wave functions overlap. One central issue for molecular qubits is to study the relationship between molecular structure and electron spin decoherence. In order to do that, we need to build a theory which can be used to study decoherence due to hyperfine coupling in molecular qubits. Experimentally, the coherence is measured through a spin-echo decay experiment. Here, the red arrow is the average magnetic moment of the spins. Using a pulse, the spin magnetization is flipped 90 degrees, just like in the previous movie. Because the local magnetic field is inhomogeneous, some spins' precession rates speed up and some slow down. We then apply a 180-degree pulse to refocus the individual spins towards the main moment. This is similar to a race, where some runners will be faster than others, but if you change the starting line in the middle of the race and cause the runners to move in the opposite direction, then those who are behind are now ahead. Eventually, all the spins will be in the same place at the echo time. This technique is performed so that the inhomogeneity of the external magnetic field no longer causes decoherence. So then it would only depend on the interaction of the electron spin and its environment. In this project, the spin-echo decay was calculated. I used DFT to give us deeper insights about the electronic structure in Van-Adel complexes. DFT is an approximate quantum mechanical method that computes the electronic structure of many body systems. It is a good balance between speed and accuracy among all the computational quantum mechanical methods. We use the functional to turn the density into the energy of the system, but nobody actually knows what the functional looks like, so we have to make approximations to it. In this project, I used two different functionals. BP is used by metals, or used for metals by material scientists, and B3-LIP is used for molecules by chemists. So here are our 4 Van-Adel complexes. These complexes were synthesized by Dr. Friedman and her lab at Northwestern University. Their electron spins were identified as potential qubits, and they all have a charge of -2 and a spin of 1/2. In this paper, they measured the T2 and plotted it as a function of the average distance between vanadium and hydrogens. Closer up, you would expect stronger hyperfine coupling, and therefore a lower T2, but the opposite was actually the case. They explained this phenomenon by a diffusion barrier radius, which states that within a certain radius, the nucleus is so strongly coupled to the electron spin that they do not contribute to the decoherence of the electron spin. In this project, we are trying to build a theory of T2 based on our ab initio calculations of hyperfine coupling to comprehend this unexpected trend, which allows us to better understand the diffusion barrier. These are the net electron spin densities that I generated through DFT calculations. As you can see, the spin densities do not change as the size of the molecules grow. These pictures show us that the spin densities are localized around the vanadium atom and behave like d orbitals for all 4 complexes. The d orbital is in the shape of a spherical 4-leaf clover. We have confirmed that we can treat the spin densities as localized d orbitals. When compared to experiment, B3-LIP appears to be a more accurate functional than BP, which is expected because B3-LIP is specifically designed for molecules. Looking at the hyperfine coupling values for vanadium, B3-LIP is closer to the experimental value than BP. These 2 graphs are 2 types of fits that I did on the same data set, power and exponential. These 4 different color points represent the 7 hydrogens in each vanadium complex. You can see that significant deviation only happens for the first vanadium complex because the fits are much better when we ignore the smallest molecule. This deviation comes from the Fermi contact term, since for the larger molecules there is little deviation. This means that Fermi contact can be modeled through spin-dipole interactions alone when the molecule is large enough. Here, spin-dipole is proportional to 1/r cubed, which is expected. Looking at the graphs, we can see that the power fit is better than the exponential when you look at the root mean squared values. So the main purpose or the ultimate goal of this project was to calculate the decoherence as a function of time. The interesting thing is we can calculate the decoherence of electron spins using the dynamics of nuclear spin. In this equation, the dynamics of nuclear spin have been solved exactly. Here, the nuclear wave function is J plus and J minus, and rho is the density matrix for the electron spin. The decoherence is the off-diagonal element of the electron spin density matrix. This model is better than the phenomenological model of a diffusion barrier radius because it is based on the time-dependent Schrödinger equation without further approximation. The main takeaways of this project were that electron spins are localized in these complexes and that the dominant hyperfine coupling comes from the vanadium atom. The decoherence of the electron spin can also be calculated from the dynamics of nuclear spin. And further details are given in Dr. Chen's talk, which is right after mine. And I wanted to thank Dr. Chen and Dr. John and the PI at the REU for letting me work on this project. Yeah, and that's it.
Okay, thank you. Do we have any questions for this talk? Okay, so I'm wondering, you said you can identify the effect of the Fermi contact term. Can you quantify that in some way?
Well, I don't think we really tried to do that because like that just like wasn't the main goal of our project in a sense.
Okay.